This is Kimi-K2 running on a 4-node Framework Desktop cluster with AMD Strix Halo APUs. Kimi-K2 is a state-of-the-art mixture of expert model with 1 trillion parameters, 32 billion of which active at each time. Here I'm using a Ansloth Q3 quantization spread across 4 Strix Halo nodes, each with 128 GB of unified memory for a total capacity of 512 GB addressable by the cluster. Those of you that follow the channel might remember that some months ago I published a video where I documented how to connect two Strix Halo systems, my Framework Desktop and the HP Mini workstation, and how to run LLMs on this setup using llama.cpp with its RPC backend, which is the easiest way to cluster these units together for LLM inference. This video is meant as a quick update to show how things look when scaling up to 4 nodes, and I want to thank Alex Ziskin who gave me access to his Strix Halo cluster with the 4 Framework Desktop Motherboards that I'm using in this video. Now, when I got access to the cluster, there were some issues, and this was mostly due to the ROCm stack on Strix Halo being inconsistent, with incompatibilities between the AMD GPU driver in the Linux kernel, the Linux firmware package, and ROCm itself. I documented that situation in a lot of detail in a separate video, including exactly what broke, why it broke, and most importantly, what works now. If you want the full technical breakdown, that video is the best reference. But in a nutshell, the setup I'm showing uses Fedora 43, Linux 6.18.3 and Linux firmware 2025-11.11. This allows to run all of the llama.cpp toolboxes with all of the backends. You can update to kernel 6.18.4 or newer, but in that case, you might only be able to use ROCm 7.2 or any of the ROCm nightly builds from the ROC. Again, check the other video out for more details. Now, once all was stable, I wrote a small orchestration script that allows the master node to deploy models across the cluster so that I didn't have to manually run the RPC server on all of the hosts. That script is available in my AMD Strix Halo toolbox repository. So, to run Kimi-K2, you need to get the quantized gguf weights from Hugging Face, and here I'm downloading them with a single curl command that I leave in the description, and be warned, this will take some time. Once the weights are downloaded, I use the run distributed llama script that you can find again in my repository. Select the first shard of the model that I downloaded before. Optionally, you can also set the context size. And by default, this will try to use the ROCm 7 nightly toolboxes, but of course you can choose a different one if you want to experiment. Hit run, and this will connect over SSH to all of the nodes in the cluster, spin the RPC server, and then start llama server with the correct CLI argument so that it can use all of the nodes in the cluster. If you look at the previous video I made, I show how to do this by hand, but this script should deal with it for you without any issue. Now, llama server will first cause the memory to be allocated on each node. Then it will copy over the layers, and this will take some time, especially the first time. It'll be faster the second time as the layers will be stored in a cache locally on each node. Once all is loaded, the llama server will be up and running and listening on port 8000, and you can reach it from the browser and start playing with the web UI. To give you an idea of the performance that you can expect from this setup, I run llama bench. Now, prompt processing is how fast the model can consume a input prompt before it starts responding, and here we get around 56 tokens per second. Token generation is the speed at which the model produces new tokens in the response, and here that's just under 10 tokens per second. Consider that these numbers are with the conservative and default llama bench parameters. The benchmark feeds a medium-sized prompt before the generation starts and then generates a short response. With longer prompts and longer generations, the speeds will of course go down. Another state-of-the-art open-weight model that we can run on this cluster is GLM 4.7. GLM 4.7 is a mixture of expert model with approximately 358 billion total parameters, of which 32 billion are active at each step. Here I'm using the Unsloth Dynamic Quantization Q8KXL. This is a very high quality quant, but it still fits comfortably in the 512 gigabytes available across the 4 Strix Halo nodes in this cluster. The workflow is exactly the same. I download the quantized weights from Hugging Face, and then I use the same run distributed llama script from my repository. I point it at the first shard of the model, set the other parameters as I want, and then I hit run. The script brings up the RPC servers on each node over SSH, loads the layers into memory, and then starts llama server with the right arguments. And there it is, GLM 4.7 running slowly but in a stable way. I also benchmarked these with Llama Bench. Here I get about 50 tokens per second in prompt processing and slightly under 5 tokens per second during token generation. This is slower than the Kimi-K2 we saw before, and the main reason is quantization. Kimi-K2 was running with 3-bit weights, while GLM here uses 8-bit weights. On Strix Halo, that directly shifts the bottleneck to memory bandwidth, since more data has to be moved for each token. As I discussed in the earlier clustering video, there are two main limitations at the moment for scaling llama.cpp across multiple machines. With llama.cpp RPC, the model is essentially split sequentially across nodes. One node runs its layers, then hands the activations over to the next node, and so on. Only one node is active at a time. And on top of that, it uses Ethernet, which introduces latency. It works and it's useful, but it's also not the most efficient. But what if we could have a genuinely low latency interconnect rather than Ethernet? In that case, we could switch to a different approach entirely and use vLLM with Tensor Parallelism. That's a fundamentally different execution model, and it's why performance scales better in setups like the dual Radeon 9700 system that I showed in a previous video. It turns out that the Framework Desktop has a PCI Express by 4 slot, and you can shoehorn into it an Intel E810 network card. The E810 is a data center card that supports RDMA, which allows machines to access each other's memories directly with very low latency, essentially bypassing the TCP/IP stack in the kernel. So, over the next few weeks, I'll be experimenting with connecting two Framework desktops over with the RDMA using the E810 card and running vLLM with Tensor Parallelism. As usual, I share all I learn, including a tutorial on how you can do the same yourself, and of course, detailed performance benchmarks. So, if you are interested, don't forget to play the YouTube game and support the channel in all the usual ways. That's all for now. See you next time.